There's a link on your website under screencast, and so I'll put those there when that time comes. See, there are none there now. They're all deleted.
I saw that.
Oh.
I noticed that too.
What's that?
No, I went there and I'm like, oh, video.
Yeah, I'm sorry. You know, really the reason is like y'all have some of the same clicker questions that my online class has, and I didn't want to post the solutions to all those clicker questions before they had to do them, but now they're ahead of y'all, so because we just sort of go at a little faster pace in that class. So if you really want to know my excuse, that's my excuse.
Also, there is one.
Uh-huh.
I was saying, so there isn't.
Yeah, but it's not a real excuse. It's just me being lazy, not making any questions.
Excuses are like buttholes. Everyone has one.
Yeah. All right. So we'll work through some more force problems today. But first, I just want to sort of go over the units of force and a few other things. The unit of the force is the Newton. Yeah, the Newton. Not like the Fig Newton, but like the scientist Newton, Isaac Newton. And so anytime you have a unit that's a person's name, whenever you abbreviate it, you capitalize it. So that's just a little grammatical fact. So when you write out the unit, it's lowercase, but when you capitalize, it's capital N.
I wonder how many Fig Newtons it would equal to.
I don't know, about 20 or so to make a Newton, I think. In the U.S., what's the unit for force? All right, it's the pound. We often use the unit for pound to denote mass, or when we try to talk about it in terms of mass, but it's really the unit for force. Of course, it's abbreviated for reasons that I don't know, LB. Sometimes you see a hash mark like that. In newtons, people weigh about 700 newtons. Just to give you a rough round figure, a small apple is about a newton. A newton, 1 newton, is about a quarter of a pound, a little less than a quarter pound, but it's about a quarter pound. So, I think it'd be really great. I don't think a student's ever done this, but I always propose it, is that you could do like this little skit where you go into McDonald's or whatever, and they have that famous hamburger. What is it? The quarter pounder. So instead of asking for a quarter pounder burger, you could say, I want a Newton burger, and see what they say. Say what? It's a quarter pound.
You couldn't in there. You'd have to continue with the manager involved and see how many people didn't know.
Right. Does anybody know the British unit for mass? This is just an interesting bit of trivia. It's the British unit for mass. Anybody know?
Wait.
It's not pounds. That's weight, right? So what is it?
Slug.
Yeah, it's a slug. So the British unit for mass is the slug, which is really like when we talk about 5 pounds of sugar or whatever, we should really use the slug, because that's really what we're concerned with, not the weight. We want to know the amount of material within that package. But who wants to buy 5 slugs of sugar, right? So I'm not sure why it never took off.
I wonder if there's a joke they have a glass slug filled with something.
Yeah.
Look at this.
Well, let's try these couple of questions. True or false? It is possible to have motion without a force. Is that statement true, or is that statement false? I'll stop at 35. It's possible to have motion. That statement is true. Right, because I can have, this goes back to Newton's first law, right? That if an object is in motion, it will continue in motion unless it's acted upon by a force. So if I have an object in motion, it's going to continue that way. Let's try this one. If an object isn't moving, then no force acts on it. Is that statement true or false? You can think about this in terms of, forces don't cause motion, they change motion. Right? So they change the way you move. Alright, let's stop this. Stop at 30. An object isn't moving. Okay, that's a false statement. That's correct. Because like you're moving, right? Or you're not moving, right? You're stationary, but you have forces acting upon you? Yeah, you have lots of forces, right? You have weight, you have the normal force, you have all this jazz. So that's a false statement. All right, let's move on to Newton's third law. So we've had Newton's first law, that was the law of inertia, right? That if an object's in motion, it stays in motion unless a force acts upon it. If an object's stationary, it will stay stationary unless a force acts upon it. Then we have Newton's second law, which describes this relationship between force, the mass, and the acceleration. That if I apply a force to an object of a certain mass, it's going to cause it to accelerate. All right, now we have Newton's third law, which is if objects 1 and 2 interact, that means if they have a force acting on one of them, then the force F12 exerted by object 1 on object 2 is equal but opposite to F21 exerted by object 2 on object 1. Let me just draw a picture. That probably doesn't make a lick of sense to you. So let's say that I have an object here, and I have an object here, and they're pushing on one another. So this object is pushing on this object with a certain force. I'll call it F21. And then this object, the red box, is pushing on the blue box with a force. I'll call it F12. So what Newton's third law says is that the magnitude of F12 is equal to the magnitude of F21. Those are equal but opposite, so they're in opposite directions. So for example, if I push on this, then it's going to push back on me with the same force. This seems more apparent when you're looking in the vertical direction. So, oh wait, what would happen actually if I pushed on this desk and there was no force pushing back that was equal and opposite? What would happen in terms of Newton's second law? It would accelerate, right? So because it would have a net force acting upon it. But as it is right now, like I'm pushing on this desk, but there's an equal but opposite force pushing back, so they're canceling one another out. You follow me on that? Yeah. All right. So we can also have this in a vertical sense. Say I have a block here. I have a force that's acting downward on it. That's the force weight. And then I have another force that's equal but opposite in the other direction. We call this the normal force. We'll talk about this in just a bit. All right. So this is happening to you right now. Like you're sitting in a chair and you have a force that's pushing back upon you that's equal to the weight. We also saw this with the law of gravitation, right? That if we had two objects that were, did we do that yet? Universal law of gravitation? No. Or did we skip it? Oh, no, we haven't done that. Are we going to? All right, we might at the end of the chapter. We'll see. So the result of this law is that there can be no isolated force. There can be no isolated force. So anytime you have one force, you're going to have an opposite force. That's called the normal force. We'll come back to this in just a bit. Can I see somebody's book? Right quick. Did we go?
I found this one right here in 163. It says gravitation and potential.
Thank you. I'm not sure why I took that out. Well, we'll be okay. All right. So there can be no isolated force. Let me just we sort of talked about this. Let me just add it as a little caveat, or not a caveat, but just sort of an additional thing. You know, if you have two bodies of mass, here and here, they exhibit forces. These are gravitational forces. Remember, what type of force is this? Is this a contact or a field force? This is a field force, right? A field force doesn't require contact between two objects. And so we have these forces. These are also equal and opposite, so they also obey Newton's third law. And these are equal in magnitude, but opposite in direction. So, anyway, the result of this law is that there can be no isolated force. That anytime you have one force, that there has to be a second force. It doesn't matter if it's a contact force or a field force. I think that's kind of cool, right? That you can have no isolated force. Can think about that for the rest of the day. What about the force due to gravity exerted on you by the Earth? Is that an isolated force? So say this is the Earth, and here you are. You're standing on top of the world, and the Earth pulls down on you with approximately 700 newtons or so. Is that an isolated force? Seems to be. Why is it not? So what is it?
I mean, the force is between you and the cure of the Earth.
Like the center of the Earth?
Yeah.
Yeah. Okay. But is that an isolated force? Is there another force that's involved? Yeah, Jose?
I still don't do what you mean by isolated.
That if you have one force, it can't be all by itself. That it has to have a second force that's equal but opposite. Sean?
It's interacting with the field forces between.
Okay, well that's a separate set of forces, right? Between the Earth and the Moon.
I guess like if it was isolated, we couldn't stand up, we couldn't support ourselves. It would.
Okay, I'm not sure I understand my question.
What about
We're what?
Force against gravity.
No, that's the book. Let me just see what I'm looking for. Is that okay? How's it?
I was gonna say what about the weight too?
Okay. Yeah, so what I'm trying to get at is that if the Earth is pulling down at you with 700 newtons, then you're also pulling back up on the Earth with 700 newtons. Yeah. So like we're all walking around holding up the Earth with 700 newtons of force. That's kind of a cool idea too. That you're actually, the Earth is attracting you, but you're also attracting you. I think that's good. All right. Now, contact forces, so field forces obey Newton's third law. But contact forces also obey Newton's third law, and the result of this is the normal force. I've already drawn a picture of this, let me draw it again. Say I have an object that's sitting on a surface. It has a certain weight, Fw, and there is an equal and opposite force that is called the normal force. I'll call that Fn, and it's from the surface of the table in this case that's pushing back up on the block. Does anybody know what normal means? What does normal mean?
Force of gravity.
No, not the force of gravity. What's the definition for normal?
Oh,
There are a couple definitions, right? What's the first, the usual definition?
The average, pretty much.
Right, it's like what's usual, right? What's normal? What's the second definition? The mathematical definition for normal? Hmm? No, it means perpendicular. You ever heard this? That if you have a line that's normal to a surface, it's perpendicular to the surface. So normal means perpendicular, and in fact the normal force is always perpendicular to the surface. So normal is the same as perpendicular. That's the definition of it. You should try today to use the word normal in a sentence, but with that definition. Like,
I don't use perpendicular.
yeah, we don't use perpendicular that often either. Now, if I wanted to calculate the normal force, going back to this scenario, I have Fn, Fw. I can solve Newton's second law. The sum of the forces in the y direction equals may. Since the acceleration is 0, the sum of the forces in the y direction equals 0. That is, the normal force minus the weight equals 0, or the normal force is equal to the weight. And that's often the case whenever I have an object that's on a flat surface, that the normal force will equal to the weight of the object. But it's not always the case, not always. And we'll see some examples we'll work through where that's the case. Can you think of a way that I might either increase or decrease the normal force on an object? Think of a couple of different ways. How could I increase the normal force of an object that's sitting on a flat surface? Could you do what? No. Could you do what, Scott? What could I do to increase the normal force of an object? I can increase its mass, right? That would increase its weight. And so, but then the normal force would still equal the weight. Right? But what else could I do?
Place it on another planet.
I could place it on another planet, yeah. That would increase its weight.
Yeah.
I could just push down on it, right? Yeah, if I push down on top of it, that would increase the normal force. So for example, if I added a force here on the top of it, pushing down, then I would have Fn minus Fw minus F would equal 0. So Fn would equal Fw plus F. Or I could decrease the normal force by pulling up on it slightly, but with a force that's less than the weight, right? And that would decrease it. I already said this, but the normal force is always perpendicular to the surface. So in the case of an inclined plane, see, I might have a picture. I do have a picture. So in the case of an inclined plane, the normal force is going to be perpendicular to the surface. So notice here I have the normal force drawn, and it's at an angle of 90 degrees to the surface. We're going to be doing a number of inclined plane problems. They're nice problems because they require you to resolve vectors into their x and y components and deal with vectors in 2 dimensions. So let's just first look at the normal force. And in the case of an inclined plane, the normal force is going to equal some component of the gravitational force. So let's imagine this. I have the normal force and I have the weight. The weight drawn here. The weight vector, the force weight, is always drawn towards the center of the Earth. I can draw my x and y axes. I've already done that here. This is my x-axis. Here's my y-axis. Notice what I've done to the coordinate system here. What have I done? I've rotated it. So we talked about this back in chapter 1, that you can rotate these coordinate systems however you want. And so we've rotated it here. And let's say that this angle is equal to 30 degrees. Then what is this angle equal to?
60.
Right, that angle has to be 60 degrees. If you look, you see you have a triangle here. Right, so that if this angle is 30, this angle has to be 90 minus 30, or 60 degrees. Now I can draw my coordinate system over here, label my vectors on it. I have my normal force, and then I have my weight. I know that this angle is 60 degrees. So I'm laying out a process that we'll take when we're working through these problems. The first step is to label all the forces. And you'll follow this on all of these problems. The second step is to draw a vector diagram. That's what I've done here. Sometimes you might combine these 2 steps, but at least as you're just learning to do these things, I would not combine them, just do them separately. You draw your vector diagrams where you pick your coordinate system, you label all of your vectors with the proper angles from each of the axes. And then your third step will be to resolve the x and y axes. See, I'm going to draw that down here because it's actually related to this problem. So I resolve my vectors into their x and y components. So I'm going to have FW times what to get the y component? Times the sine of 60, right. And then I have FW times what? Cosine of 60. And then I have the normal force. Alright, so I resolve the vector, that's my third step. And then my fourth step is to apply Newton's second law. And remember, we have Newton's second law, the sum of the forces in the x direction equals max, and the sum of the forces in the y direction equals may, and we can say the same for the z direction, but it's only 2 dimensions here. So let's just look first at the y direction. I get Fn, that's up, minus Fw sine of 60 equals may. What's the acceleration in the y direction for this object? No, not negative 9.8. Now notice, what is this object doing? Like, can you describe its motion just in words?
Sitting on plane.
Well, it's not, I don't know, is it stationary?
It's asking, must be applied.
Okay, we don't have an applied
So
force
that-
yet. I just have the forces that are acting here. What's the object doing? Right, it's sliding, right? It's like a kid on a slide. He's sliding down. So I have it drawn here because I know that it's sliding down because on the x-axis, which is the plane of the incline, notice that there's only one force. So there are these unbalanced forces causing it to move down the inclined plane. So it's like a kid on a slide. However, what is the acceleration in the y direction? I know the acceleration in the x direction is some positive value, sliding down the incline. But what is it in the y direction? Is he moving in the y direction? No, he's not. Not at all. So what's the acceleration in the y direction? Is 0. Right. So the acceleration in the y direction is 0. And so I can say then that Fn equals Fw sine of 60. All right. So here the normal force is the y component of the weight, which I have it right here. The y component of the gravitational force. Now let's look at this example. This is from a Kaplan MCAT problem. If I have the mass of this box is 10 kilograms, then what force F directed up the inclined plane must be applied so that the box is stationary. So I want to know what must this force be so that the box is stationary. I'm going to add it to my vector diagram here, F. I add it to my resolve vectors. Fortunately, it's on the x-axis. So do it there. And now I want to know what must that force be so that it's stationary. I'll give you all a few minutes to work that out. So what must the force be so that the block remains stationary? My mass is 10 kilograms. Somebody have it? What is it? 5? No, you're just off by 1 place. Somebody else have it? What's the weight of the block? That's the mass, right? What's the weight?
98.
Right, 98 newtons. 10 times 9.8 is the weight. So So my weight of the block is mg, 10 98 newtons. Now, I know that for it to be stationary, that these two forces have to be equal and opposite. If I were to write this in terms of Newton's second law, I'd say Fw cosine 60 minus F equals 0. And so F, which is what I want to know, equals Fw cosine 60. Of course, cosine 60 is what? Is a half, right? It's a half. So a half of our force weight is 49 newtons. I know that's supposed to be a fairly simple problem, but it lays out the technique that you'll follow. That is that you label all the forces on an object, draw the vector diagram, resolve the vectors into their x and y components, and then apply Newton's second law. And then once you get those four, I mean, that's all of statics and dynamics, basically, that you follow those 4 steps. We'll do some more complicated examples. But I would expect your quiz to be more complex than that.
Well, sir,
Yeah.
when you crouch and jump up, how will the normal force change?
I'm sorry, when you what?
When you crouch, CROUCH,
When I crouch?
yeah, and try to jump up,
Uh-huh.
how will the normal force change?
Well, that's a good question. So, like if I do a standing jump, like if I do like this, you mean?
Yeah.
And jump up?
Yeah.
Right, what happens to my normal force in the process of accelerating upward? Increase or decrease or stay the same?
The normal force will decrease, but another force will decrease because you're overcoming the force of gravity.
Well, let's draw the vector diagram, right? So here I am. I'm crouching. All right, I have a force acting on me. I have my force weight. I also have my normal force acting upon me. I'm accelerating though, right? Which direction am I accelerating? I'm accelerating upward. So in the moment that I'm actually pushing up with my legs, then I'm accelerating upward. So if I apply Newton's second law here, the sum of the forces in the y direction equals may. Then I have Fn minus Fw equals may. And before, acceleration was equal to 0, but now it's actually positive. So I find that my normal force is equal to my weight plus my mass times my acceleration. So how does my normal force when I'm crouching and jumping compared to just if I'm just standing around? What's the normal? It increases, right? And it's actually that unbalance of forces that's causing you to move upward. That I have that normal force, which is larger than my weight, causing me to accelerate upward. Is that clear? Yeah, that's a good question. Let me fix that question. All right. A quiz question, I'm sorry. A quiz question. Like for multiple choice. All right. Let's do this question. And then we'll move into the concept test. So here, this is the same situation. I have my normal force, my force applied of the inclined plane, and my force weight. I want you to tell me which of these equations is correct regarding these forces. So applying Newton's second law, which of these equations is a correct application of that law? Be careful with your angles. Notice sometimes I use sine of 30 and sometimes I use sine of 60. Remember how the angles are measured. I'll stop at 130. 130. Let's guess if you don't know. Let's see, it's right. There are a couple reasons why B is not right. I'll show you why that is. But first, let's just go through each of them. I'll show you why each of them is not right. Here I have Fn minus F. Look, these are on completely different axes, so they're not related at all. So I can just take that out completely, because Fn is on the y-axis and F is on the x-axis. Let me go ahead and draw my coordinates here. There's my x, there's my y. I know that this angle is 60 degrees. Here I have Fn minus Fw sine 30 equals max. I could make this equation correct in a couple of ways. First, I could change this 30 degrees to 60 degrees, and that would be the y component of the weight. So that would be this vector, Fw sine of 60, and this would be Fw cosine of 60. But that option B still is not correct. Why is it not correct? Even if I make that change? What's that, Joseph? No, it wouldn't be correct with cosine of 60 because the normal force is in the y direction. And then you would have a vector on the x-axis and a vector on the y-axis, and they're not related. Why is this still not correct? It's max, right. So it has max. If you had may, then it would be correct. C is the correct one. I have the normal force is equal to Fw sine 60. That's coming from the sum of the forces equals Fn minus Fw sine 60 equals 0 because the acceleration is 0, so those two forces are equal. And here I have the weight is equal to Fn. That's not correct because it's excuse me, the y component of the weight, not the actual weight. Good multiple choice question for the test. Let's do some more clicker questions with the concept test. We haven't done that at all for this chapter yet, have we? I think we have. There's a lot of them there, so let's just do a few of them. Say this pony went into a bar, and he said to the bartender, "Hey, give me a drink." And the bartender said, "What?" And the pony said, "Give me a drink." And the bartender said, "What?" And he said, "Give me a drink." And the bartender, he didn't hear him. And then finally the pony said, "I'm sorry, you're gonna have to forgive me. I'm just a little hoarse." Y'all have heard that one before, right?
So, did you wake up every morning thinking, which one should I tell today?
No. All right. Book is lying we haven't done these, correct? Mm-hmm. Okay. Book is lying at rest on a table. The book will remain there at rest because what? Stop at 40 seconds. 40 seconds. And we're all over the place. So, okay, A is not correct. There is a net force, but the book has too much inertia. If it's lying at rest, then there is no net force, right? Because if there's a net force, it has to be accelerating by Newton's second law. So A is not correct because there is no net force. B is not correct because there are forces acting on it, right? There's at least the weight and the normal force, and then maybe other forces that we're not even noticing. It does move. That doesn't make sense. It's not moving. There is no net force on the book. D is the right answer. And E is not right because there is no net force. So D is the right answer.
You got an interesting thought for
seen. It's simply moving from gravity from a million miles away. It's pulling, Mars is pulling on my hook.
All right, hockey puck slides on ice at constant velocity. What is the net force acting on the puck? Stop at 45. All right, very good. The answer is E. If it's moving at a constant velocity, that means the acceleration is 0, so the net force is 0. So that's a very Newtonian way of looking at things, but all those others are sort of, you know, Aristotelian way of thinking. You put your book on the bus seat next to you. When the bus stops suddenly, the book slides forward off the seat. Why does it do that? Did y'all ride the bus when you were kids?
I wish I didn't.
We had to ride the bus for like 2 hours because we lived way out in the boonies. It was like the equivalent of cutoff or whatever. But having to ride all the way to Thibodeau to go to school. I'm sorry, is anybody living in cutoff?
Yeah.
Oh, okay, I'm sorry. But I mean, it's nice down there. But I just meant we were really far away from town. And we had this bus driver. Do y'all care? This is not related. Sure, Caroline. You do care. We had this bus driver, Evelyn Burke was her name. She was, you know, older lady. She's really old now. She's like 90 or whatever. I saw her recently. And with my two brothers. I have two older brothers. They're 6 and 8 years older than me. And they were, I don't know, like when they were in school, they didn't really like school that much. This might shock you, but like I really liked school a lot. And I think it's not getting in too much trouble when I was in school. But they were bored and they, I don't know, they got in trouble. My oldest brother actually got expelled from the bus. Like he could not ride the bus for the rest of his career or whatever. Because he did a bunch of stuff, but like on his last day on the bus, he started lighting cigarettes and handing them out to all the little children. And his nickname was Moondog. Can you imagine why his nickname was Moondog? I don't think people really do this anymore. What, Eddie? He would moon people, in fact. And he mooned the bus one time, but she tried to get him in trouble for this because she knew that it was him, though she couldn't see his face, obviously. She could see something else. But anyway, she saw us and she said, I don't like you. I don't like you. You might be okay. Anyway, buses.
Yeah, on
I'm going to stop this, okay?
that was a long question.
No, this is not right.
It's not.
It's because gosh, nobody got the answer right. Because I was too busy telling you that story, right? Yeah. What's that?
I never got to my answer.
Yeah, the answer is B. No net force acted upon it. Newton's first law, right? It's the bunch of Aristotelian folks. Because it's moving at a constant velocity, and it's going to continue moving at a constant velocity unless a force acts upon it. And when a force doesn't act on it, it keeps going and it slides off the seat when the bus stops. Normally that doesn't happen, right? What is the force that acts on these books? The what? The what? No, not inertia. Inertia is what causes it to go forward. If it stays on the seat, what's actually keeping it on the seat? The frictional force. We'll get into that soon. No, it's not the normal force, but that's related to friction. We'll see that soon. All right. It's very hard to sort of break these ideas in your head. You have to think about motion in a different way. All right, you kick a smooth, flat stone out on a frozen pond. The stone slides, slows down, and eventually stops. You conclude which of these? Now, Aristotle would look at the situation and say, well, it just wanted to get back to rest. What's the real answer? Stop at 55. Very good. All right, consider a cart on a frictionless table. Given a push and release, what will happen to the cart? Yeah. Means that it's completely smooth, that there's no resistive forces, no frictional forces. Right? You understand? All right, I'll stop at 55. Very good. Forever, right? Or until a force acts upon it. Forever. Or until a force acts
Into a
upon it.
concept that can be, that we don't really know what forever is. We pick a finite value really, really freaking far away and call it forever.
All right. What about for constant acceleration? What do we have to do? Stop at 50. Very good. So to accelerate, you have to have a force applied.
You accept giving it feet as an answer.
Giving it feet? That wasn't an option. Sorry, we don't take right-hands on these. Our very large truck sits on a frozen lake, assume no friction between the tires and the ice, and this fly comes along and smashes into the windshield. I want to know what happens to the truck after the event of smashing into the windshield. What does the truck do? Doesn't matter.
Yes.
Doesn't matter.
Doesn't matter? Okay, now I know the answer.
It's not a trick.
Oh, please.
Stop it.
So if the truck is not moving at all,
Right, it's completely stationary.
it's
All right, 50.
What law are we basing this off of?
It's B. Don't know what the answer was. Just being ornery about it, huh? No, so this fly, if it smashes into this truck, it's going to impart a certain force to the truck. It's going to be minute, right? Very small. But it will impart a force to it, which will cause the truck to accelerate. Now usually there's enough friction between the tires and the surface in order to not accelerate, to oppose that force. But in this case, we're assuming no friction at all, which will cause the truck to accelerate backwards. And then after that event of smashing into the truck, it's going to move at a constant velocity. Rob?
But you're saying, you were talking about the force pushing back on something, so if you give it a force, like if you push it on that table, even if it didn't have friction on the bottom of it, it still got weight. So if a fly is too light to push something forward, the force this force coming back on it won't move it, right? Or am I thinking about that wrong?
That's what I was thinking. Yeah, that's what I was thinking.
No, but the weight of the truck is kind of wide, right? So that's...
I'm thinking more like on like you see these videos at the space station when you got like fruit floating, you know, so like there's no weight. But I'm thinking, you take weight out of the equation, friction out of the equation, and you just focused on the forces. So
Yeah, so if you were
is
in...
that the kind of conceptually what we're talking about?
Yeah, so that's probably a better way to think about it. Is if say you have a truck floating in space, and a fly comes along and hangs against the truck, that's going to cause it to accelerate backwards and then move at a constant velocity.
I just cannot picture it. I don't.
Okay.
A fly hitting a truck?
All right. Well, let's stop there, guys. I'll see you on Monday. Have a good weekend.
You too.
Have a fruitful weekend. You got any working?
So we're working at a
No what?
We're working at Herd Alone.
Right.